Welcome back, everybody. Today we're going to cover the resources on the Earth. There's a section on human impacts in the standards, so we need to cover them for the next two lectures. So we're going to start off with some of the resources of the Earth. So sun, wind, water, and geothermal energy have been around since the Earth was formed and are considered renewable or self-sustaining. However, they can be difficult and often expensive to harness, and large amounts are needed to produce only small amounts of electrical or fuel energy. Oil, natural gas, and coal are efficient energy sources because with small amounts we can produce relatively large amounts of electrical or fuel energy. They are non-renewable energy sources, which means that once it's used up, it can't be replaced. Pollution is also created when oil and coal are used for energy. Fossil fuels are the major type of non-renewable resource. Fossil fuels or mineral fuels are fossil source fuels. That means that it's hydrocarbons found within the top layer of the Earth's crust. It's generally accepted that they formed from the fossilized remains of dead plants and animals by exposure to heat and pressure in the Earth's crust over hundreds of millions of years. This is known as the biogenic theory and was first introduced by Mikhail Lomonosov in 1757. Fossil fuels are non-renewable resources because they take millions of years to form, and reserves are being depleted much faster than new ones are being formed. When coal, natural gas, or oil are burned, they release gases into the atmosphere. Carbon dioxide is a greenhouse gas, trapping heat in the lowest part of the Earth's atmosphere. This contributes to global warming, which means that the average temperature of the Earth slowly increases and affects ecosystems across the globe. Sulfur dioxide is another gas that is released by the burning of these fossil fuels, and it's a key contributor to acid rain, primarily in the northeastern United States, and also in other countries. For example, China's acid rain problem is really intense. Nitrogen oxides contribute to acid rain and smog, as well as health issues such as lung inflammation, immune system changes, and eye irritation. There are three major forms of fossil fuels. All three were formed many hundreds of millions of years ago, before the time of the dinosaurs. Hence the name fossil fuels. The age they were formed is called the Carboniferous period. It was part of the Paleozoic era. Carboniferous gets its name from carbon, the basic element in coal and other fossil fuels. The Carboniferous period occurred from about 360 to 286 million years ago. At the time, the land was covered with swamps filled with huge trees, ferns, and other large leafy plants. The waters and seas were also filled with algae, which is the green stuff that forms on stagnant pool water. Algae is actually millions of very small plants. All fossil fuels, whether solid, liquid, or gas, are the result of organic material being covered by successive layers of sediment over the course of millions of years. Some deposits of coal can be found during the time of the dinosaurs. For example, thin carbon layers can be found during the late Cretaceous period, which was 65 million years ago, the time of Tyrannosaurus rex. But the main deposits of fossil fuels are from the Carboniferous period. Fossil fuels supply over 80% of the world's energy needs. Coal is derived from the accumulation of partially decayed land plants. As the sediment solidifies into rock, the organic material decomposes under the influence of great pressure and high temperatures. Coal is an abundant fossil resource that consists mostly of carbon. The energy content, which is measured in BTUs per pound, ranges from 5,000 to 15,000 depending on the type of coal. Coal reserves are located all over the world. Electric utilities consume about 87% of the total coal produced. In the United States, coal is used to generate more than half of all of the electricity produced. It's also used as a basic energy source in many industries and as a heating fuel. The U.S. is one of the top exporters of coal in the world. Most exported U.S. coal goes to Western Europe, Canada, and Japan. Coal is recovered from the earth by surface mining or deep mining. Surface mining, which is also called strip mining, is less expensive and usually occurs on flat land. Deep mining requires digging shafts and tunnels to get to the coal seams. Automation of deep mining has helped to counter its safety and health hazards. However, coal mining has killed many, many, many people every year around the world. Coal can be gasified to form a synthetic fuel similar to natural gas. It can also be liquefied to make a synthetic crude oil. To date, it has not been economical to make synthetic fuels from coal on a large scale. As processes become more efficient, the use of synthetic fuels may become more economical. Oil comes from crude oil, which is a mix of hydrocarbons with some oxygen, nitrogen, and sulfur impurities. 1 barrel of oil, which is 42 US gallons, can provide about 6 million British thermal units, or BTUs. Crude oil reserves are found all over the world, but the Middle East alone has about 63% of the known reserves. Of the oil consumed in the United States, most is used in transportation, and much of the rest goes to industrial, commercial, and residential uses. Crude oil is used to produce not only a range of fuels, but also petrochemical ingredients for plastics, inks, tires, pharmaceuticals, and foods. High-tech oil exploration technology and practices have led to the discovery of as many new reserves as have already been used. To make the most of this valuable resource, energy producers are developing more efficient refinement methods. Product makers are finding more efficient ways to use petrochemicals, and manufacturers are developing more efficient cars. New techniques of locating and extracting oil from the earth are also making it possible to recover oil that was once too expensive to produce. Oil is usually recovered by drilling wells through non-porous rock barrier that traps the oil. In general, about 30% of the oil trapped can be economically recovered by pumping. Secondary recovery can remove about another 10% by flooding the well with high-pressure water or gas. Another 10% can sometimes be recovered with tertiary methods that heat the oil to scrub it out. About half of the oil is still left trapped in the rock. Oil producers are continually seeking economical ways to recover more of this oil. The oil refining process separates crude oil into different hydrocarbons and removes impurities such as sulfur, nitrogen, and heavy metals. The first step is fractional distillation, a process that takes advantage of the fact that different hydrocarbons boil at different temperatures. In a tall tower called a fractionating column, crude oil is heated until it boils. Horizontal trays divide the column at intervals. As the oil boils, it vaporizes, and each hydrocarbon rises to a tray at a temperature just below its own boiling point. There it cools and turns back into a liquid. The lightest fractions are liquefied petroleum gases such as propane and butane, and the petrochemicals used to make plastics, fabrics, and a wide array of consumer products. Next come gasoline, kerosene, and diesel fuel. Heavier fractions make home heating oil and fuel for ships and factories. Still heavier fractions are made into lubricants and waxes, and the remains include asphalt, which is used for, of course, paving roads. The refining process then continues with heavy fractions converted into lighter fractions. In most cases, cracking processes are used to transform large, heavy hydrocarbon molecules and make the smaller, lighter molecules such as gasoline and jet fuel. Better refining technologies have made it possible to produce over 21 gallons of gasoline from a 42-gallon barrel of crude oil, which is a remarkable advance over the industry's early days when a barrel of oil yielded just 11 gallons of gasoline. Oil shale was never buried deep enough or heated enough to form crude oil. Its hydrogen content is between that of coal and crude oil. Concentrations of oil are low, so that at most 1 barrel of oil can be recovered from 2.4 tons of oil sands, or 1.5 tons of oil rocks. Huge amounts of oil shale are found all over the world. In fact, the total global resource is 1,000 times greater than the crude oil reserves. But extracting the energy value of oil shale is not practical today. Scientists and engineers continue working on ways to recover oil shale for a reasonable cost. Natural gas is component of coal and oil formation. It's used in industrial and commercial heating and cooking, and increasingly to fuel electricity generation. In a compressed form, natural gas can also be used as a transportation fuel. Natural gas is either found mixed in oil or is released from coal. Energy in 6,000 cubic feet of natural gas is equivalent to 1 barrel of oil. World reserves of natural gas are greatest in Russia, Iran, Qatar, Saudi Arabia, the United Arab Emirates, and the U.S. The U.S. consumed 19.7 million cubic feet of natural gas in 1999, nearly all of which came from domestic production. 5 states, Texas, Louisiana, Alaska, New Mexico, and Oklahoma, hold more than 85% of the U.S. natural gas reserves. However, new reserves since '99 have been found in Wyoming, and it has created a major industry in Wyoming and North Dakota. Wells for natural gas are drilled in underground reservoirs of porous rock. When it's removed from a reservoir, natural gas can either be pumped to the processing station for removal of liquid hydrocarbons, sulfur, carbon dioxide, and other components, or it can be stored in large caverns underground until it is needed. Pipelines are the main method of transporting natural gas. It can also be liquefied and shipped overseas, but this process is complex and expensive. Electrical generation by natural gas has been improved by the development of combined cycle systems. These systems put together a natural gas-fueled combination turbine with a heat recovery steam generator and a steam turbine to produce electricity in 2 ways rather than just one. The result is that roughly 60% of the heat from the natural gas is harnessed to make electricity, creating a more energy-efficient system. The United States uses about 20.8 million barrels of oil every day. Fossil fuels account for nearly 80% of our country's energy, and coal is used to produce almost 60% of our nation's electrical power and accounts for 22% of our overall energy consumption. Natural gas, a third form of fossil fuel, accounts for roughly 23% of the United States energy budget. It takes the equivalent of 7 gallons of gasoline per day for every man, woman, and child to keep this country running at its current pace. The U.S. is home to 4% of the world's population, yet consumes 26% of the world's energy. Fossil fuels, coal, oil, and natural gas currently provide more than 85% of all of the energy consumed in the United States, nearly 2/3 of our electricity, and virtually all of our transportation fuels. Moreover, it is likely that the nation's reliance on fossil fuels to power an expanding economy will actually increase over at least the next 2 decades, even with the aggressive development and deployment of new renewable and nuclear energy technologies. Developing Asia and South America are expected to have the most rapid growth rates in energy demand over the next 2 decades. In both regions, total energy demand is expected to grow by about 4% per year between 1999 and 2020. So let's take a look at what burning all of this energy actually does. Natural gas is projected to be the fastest growing primary energy source worldwide, maintaining growth of 3.2% annually during the 1999-2020 period, more than twice as high as the rate for coal. Natural gas consumption is projected to rise from 84 trillion cubic feet in '99 to 162 trillion cubic feet in 2020, primarily for electricity generation. Gas is increasingly seen as the desired alternative for electric power, given the efficiency of combined cycle gas turbines relative to coal and oil-fired generation, and because it burns more cleanly than either coal or oil, making it a more attractive choice for countries interested in reducing greenhouse gas emissions. Coal use worldwide is projected to increase by 1.7 billion short tons, or 36%, during the same period. Substantial declines in coal use are projected for Western Europe and the EU countries where natural gas is increasingly being used to replace coal, to fuel new growth in electric power generation, and for other industrial and building sector uses. In the developing world, however, even larger increases in coal use are expected. The largest increases are projected for China and India, where coal supplies are plentiful. Together, these two countries account for more than 90% of the projected rise in coal use in the developing world over. Carbon dioxide emissions are expected to rise to 7.8 billion metric tons of carbon equivalent in 2010 and to 9.8 billion metric tons by 2020. Much of the increase is expected in the developing countries, where emerging economies are expected to produce the largest increases in energy consumption, and carbon dioxide emissions are projected to grow by an average of 3.7% per year. Developing countries alone account for 81% of the projected increment in world carbon emissions. Oil consumption is also projected to account for the largest increment in worldwide carbon dioxide emissions. In 2020, emissions related to oil use are projected to be 1.9 billion metric tons of carbon equivalent, higher than the 1990 levels. The earliest known use of coal was in China. Coal from the Fushan mine in northeastern China may have been used to smelt copper as early as 3,000 years ago. Oil has been used for more than 5,000 to 6,000 years, and the ancient Sumerians, Assyrians, and Babylonians used crude oil and asphalt, or pitch, collected from large seeps at Tutul, which is modern-day Hit, on the Euphrates River. A seep is a place in the ground where the oil leaks up from below the ground, and the ancient Egyptians used liquid oil as a medicine for wounds, and oil has been used in lamps to provide light. Sometime between 6,000 and 2,000 years before the Common Era, the first discoveries of natural gas seeps were made in Iran. Many early writers described the natural petroleum seeps in the Middle East, especially in the Baku region of what is now Azerbaijan. The gas seeps, probably first ignited by lightning, provided the fuel for the eternal fires of the fire-worshipping religions of the ancient Persians. Nuclear energy is in the nucleus or core of an atom. Atoms are tiny particles that make up every object in the universe, and there is enormous energy in the bonds that hold atoms together. Nuclear energy can be used to make electricity, but first the energy must be released. It can be released from atoms in two ways, either fusion or fission. In nuclear fusion, energy is released when atoms are combined or fused together to form a larger atom, and this is exactly how the sun produces its energy. In nuclear fission, atoms are split apart to form smaller atoms, releasing this energy. Nuclear power plants use nuclear fission to produce electricity. However, in France, they have just started piloting a nuclear fusion reactor. Nuclear power plants are extremely clean and efficient to operate. However, nuclear power plants have some major environmental risks. They produce radioactive gases, and these gases are to be contained in the operation of the plant. If the gases are released into the air, major health risks can occur. They also use uranium as a fuel to produce power, and the mining and handling of uranium is very risky, and radiation leaks can occur. The third concern for nuclear power is the permanent storage of spent radioactive fuel. This fuel is toxic for centuries, and handling and disposing is an ongoing environmental issue. When a nuclear power plant goes down, it goes down spectacularly and worries a lot of people. Chernobyl in 1986 was a big one, but more recently the Fukushima plant in Japan that went down caused a lot of major problems and cleared out areas of Japan that people will never live in again. These are concerns with nuclear energy. However, nuclear energy is the single only fuel that can be used that will drop carbon dioxide emissions significantly enough to begin a cooling trend for the planet. So it's kind of a devil if you do, devil if you don't kind of situation. So now let's talk about renewable energy resources. And I know this is a long one, so bear with me. We're going to go as fast as we can. The first one we're going to cover is geothermal energy. The word geothermal comes from the Greek words geo for earth and thermi for heat. So geothermal energy is heat from within the earth. We often use the steam and hot water produced inside the earth to heat buildings or generate electricity. Geothermal energy is a renewable energy source because the water is replenished by rainfall in the water cycle, and the heat is continuously produced inside the earth. Most geothermal reservoirs are deep underground and have no visible clues showing above the ground. Geothermal energy can sometimes find its way to the surface in the form of volcanoes and fumaroles, which are holes where volcanic gases are released, or hot springs and geysers. The most active geothermal resources are usually found along major plate boundaries where earthquakes and volcanoes are concentrated. So most of the geothermal activity in the world occurs in an area called the Ring of Fire, which is around the Pacific Ocean. Okay, so for geothermal energy, this is one of those things that we're still working on harvesting. There's a few experimental projects here in the United States that are working on it. University of Minnesota is using it entirely in combination with buried buildings to heat their university. There's also some applications that are being done in Iceland. Some applications of geothermal energy uses the Earth's temperature near the surface, while others require drilling miles into the Earth. The three main uses of geothermal are direct use and district heating systems, which use the hot water from springs or reservoirs near the surface, electricity generation in a power plant that requires water or steam at very high temperatures. Geothermal power plants generally built where geothermal reservoirs are located within a mile or two of the surface, because otherwise it's prohibitively expensive to pump it. And geothermal heat pumps, which use stable ground or water temperatures near the Earth's surface to control building temperatures above the ground. We've already known about this since ancient times, and the Romans, Chinese, and Native Americans use hot mineral springs for bathing, cooking, and heating. In Iceland, there are 5 major geothermal power plants which produce about 26% of the country's electricity. In addition, geothermal heating meets the heating and hot water requirements for around 87% of the nation's private housing. In 2006, 26.5% of the electricity generation in Iceland came from geothermal and 73.4% from hydropower, and only 0.1% from fossil fuels. The United States generates more geothermal electricity than any other country, but the amount of electricity it produces is still less than 1% of the electricity produced totally in the United States. Only 4 states have geothermal power plants. California has 33, and those produce almost 90% of the nation's total geothermal electricity. Nevada has 15, and Hawaii and Utah each have 1. Southeastern Idaho is another area where geothermal would be a practical application, but unfortunately the resources are not there to harvest it. The next one we're going to look at is solar power. Solar energy technologies harvest the sun's energy for practical ends, and these technologies date from the time of the early Greeks, Native Americans, and Chinese, who warmed their buildings by orienting them toward the sun. Throughout most of history, people have considered the power of the sun when designing buildings, and after the Industrial Revolution, the practice of utilizing the sun was abandoned. Solar energy is free and inexhaustible, and this vast clean energy resource represents a viable alternative to the fossil fuels currently polluting our air and water. They also threaten our public health and contribute to global warming. Solar energy is a clean, environmentally friendly source of power. One factor I've seen is that all of the energy stored in the Earth's reserves for coal, oil, and natural gas is matched by the energy from just 20 days of sunshine. Each day, more solar energy falls to the Earth than the total amount of energy in the planet's 6 billion inhabitants would consume in 27 years, and currently we only harness about 1% of this energy. In order to harvest it, we use photovoltaic cells, or solar cells. The solar irradiance figures indicate the average annual energy available per square meter. When sunlight reaches the Earth, it's distributed unevenly in different regions. Not surprisingly, the areas near the equator receive more solar radiation than anywhere else on the Earth. Sunlight also varies with the seasons, as the rotational axis of the Earth shifts to lengthen and shorten days with the changing seasons. So the quality of sunlight reaching any region is also affected by the time of day, the climate, the cloud cover, the air pollution in that region, and also its latitude. So in other words, solar power is more advantageous in certain states than in others. The last one we're going to look at is wind power, which has been resurging in popularity in Idaho. Wind is a form of solar energy because winds are caused by the uneven heating of the atmosphere by the sun, the irregularities of the Earth's surface, and the rotation of the Earth. Wind flow patterns are modified by the Earth's terrain, bodies of water, and vegetative cover. This wind flow can be harvested by modern wind turbines and can be used to generate electricity. About 1 to 2% of the energy coming from the sun is converted to wind energy, which is enough to meet the electricity needs of the world 3 times over, and is a source of power that will never run out. The term wind energy or wind power describes the process by which the wind is used to generate mechanical power or electricity. Wind turbines convert the kinetic energy in the wind into mechanical power. This mechanical power can be used for specific tasks such as grinding grain or pumping water, or a generator can convert this mechanical power into electricity to power homes, businesses, schools, and the likes. Wind turbines are basically giant aircraft propeller blades. They turn in the moving air and power an electric generator that supplies an electric current. So the wind turbine is basically the opposite of a fan. Instead of using electricity to make wind, like a fan does, wind turbines use wind to make electricity. Wind energy is a free, renewable resource, so no matter how much is used today, there will still be the same supply in the future. It's also a source of clean, non-polluting electricity, unlike conventional power plants. Wind plants emit no air pollutants or greenhouse gases. According to the U.S. Department of Energy, in 1990, California's wind power plants offset the emissions of more than 2.5 billion pounds of carbon dioxide and 15 million pounds of other pollutants that would have otherwise been produced. It would take a forest of 90 million to 175 million trees to produce the same air quality. Even though the cost of the wind power has decreased dramatically in the past 10 years, the technology requires a higher initial investment than fossil fuel generators. Roughly 80% of the cost is the machinery, with the balance being site preparation and installation. If wind generating systems are compared with fossil fuel systems on a life cycle cost basis, counting the fuel and operating expenses for the life of the generator, however, wind costs are much more competitive with other generating technology because there is no fuel to purchase and minimal operating expenses. There is some concern on regarding the environment for wind power, however, because the rotor blades do produce quite a bit of noise. There's also some aesthetic problems, in other words, it's ugly. And there's also some birds and bat mortality by flying into the rotors. Most of these problems have been resolved or greatly reduced by technological development. However, the major challenge to using wind as a source of power is that it is intermittent and does not always blow when the electricity is needed. So most people use more electricity at night, for example, or when it's hot, or when it's really cold. Well, during those times, the wind ain't blowing. So you have to use batteries in order to harness and meet the timing of the electricity demands. Also, good wind sites are often located in remote locations which are far from the areas of electric power demand, such as the cities. So you have to get a way to get that electricity to where it's needed. All renewable energy, except for tidal and geothermal power, and even the energy in fossil fuels, ultimately comes from the sun. The sun radiates 1 trillion kilowatt hours of energy to the Earth per hour. So the Earth receives 10 to the 18th power of watts of power. And about 1 to 2% of the energy coming from the sun is converted into wind energy. That's about 50 to 100 times more than the energy converted into biomass by all of the plants on the planet. So what we're dealing with right now with wind power, which seems to be one of the key technologies we're going to focus on, especially in this state, is that we have to work on the batteries and the systems to get the electricity to where the demand is. So that's one of those things that has not yet been resolved here in the state of Idaho. Okay, ladies and gentlemen, that is it. So I know this was a long one, and I apologize. It's not really a soapboxy one. The next one is, but it'll be a lot shorter, I promise. Okay, you have a great day.